everyone, my name is Sophia Birmingham, and I will be presenting my project this summer on studying changing state active galactic nuclei with Scarlet-2, as supervised by Professor Melchior, Dr. Charlotte Ward, and Matt Sampson. So changing state active galactic nuclei are a population of variable AGNs. Variable AGNs are accreting supermassive black holes, like Miguel said, in the centers of galaxies, but they display optical and infrared variability that we can study through light curves, which essentially just plot the flux as a function of time, as we can see in the graph below. So CSAGNs, they are a population of variable AGNs that display very strong flux variability and drastic spectral changes over unusually short timescales. Astronomers believe that CSAGNs are associated with accretion disk perturbations, and we would like to study these objects in order to understand the physical mechanisms that drive these extreme spectral transitions. And we study these objects through the Zwicky Transient Facility, which observes the same region of the sky once per 3 days. So it's very useful to study how objects change in time. So we use Scarlet-2 as a tool to study CSAGNs. Scarlet-2 is a software developed by Melchior et al. That models and deblends galaxies through source separation. So Scarlet-2 implements a neural network that we have trained on real galaxy images, and it is then able to perform scene modeling on a given image. Scarlet models galaxies by performing a likelihood-based optimization and is then able to deblend sources into their individual components. We are now able to then reconstruct a given image via summing each source's individual flux. In the image we can see here, we have an observation of a galaxy in 3 separate bands or wavelengths. In the middle row, we can see that Scarlet has successfully modeled these galaxies with very little structure in its residual plots. Scarlet-2 has very large applicability. We are using it in order to measure the flux of variable objects with time and also to model these AGN's host galaxies. So the typical method for constructing AGN light curves is through difference imaging. This process subtracts out the host galaxy light from the AGN point source in order to isolate the AGN's point source. However, some issues with this subtraction method are that it leaves out the data about the host galaxy because we are simply deleting this light from the image. In addition, this method can also create noise in the light curves, as we can see below, when there is convolution with the point spread function, the AGN host galaxy, and any other point sources in the image. So this is why we use Scarlet-2 to model galaxies. We are able to analyze lower resolution and fainter CSAGNs with a reduced noise in the light curves. In addition, modeling galaxies allows us to capture and utilize information about the AGN host galaxy itself. Thus, our goal is to use Scarlet-2 with our ZTF image trained prior for the neural network in order to model AGNs and their flux. So our first step was constructing the prior that we will be then training Scarlet-2's neural network on. This prior is a simulation of a few thousand galaxies of ZTF-like galaxies from the GalSim package. Our prior simulations were based on a distribution of morphological parameters of real AGN host galaxies from ZTF. And one such distribution can be seen here in the graph. This is a distribution of a sample of AGN host galaxies, and this is plotting the axes ratios of those galaxies. So we constructed a prior that contained a wide range of different galaxies in order for Scarlet-2's neural network to be adequately trained. So once we obtained our prior of about 10,000 GalSim simulations, a sample of which can be seen here in the right image, we then trained the neural network. So now, given a real ZTF image, our neural network is able to produce models that look like real observational images on its own. And now Scarlet is able to deblend the multiple sources in an image, for example, the point source, the host galaxy, and any other object that contains flux. And now our neural network ensures that each modeled individual source looks like a corresponding real source. Next, we obtained real ZTF data and modeled these AGN's host galaxies on our newly trained version of Scarlet-2. We were then able to test a lot of new features of Scarlet-2 on very low resolution ZTF data. We did this by modeling about 1,000 variable AGNs of different sizes and morphologies. And we were then able to analyze Scarlet-2's performance by creating residual plots. We want to see residual plots such as in the image here, where there's no underlying structure so that we know Scarlet 2 is successfully modeling the observation. In this image, we have a complex spiral galaxy that we can see Scarlet 2 is successfully modeling. Next, for the main point of the research, we wanted to study the variability properties of CS AGNs and compare them to regular AGNs. So we do this by fitting the light curves of CS AGNs with a power law model and create corresponding power spectra. In the image below, we have the typical light curve of a CS AGN in two separate bands, and then we've constructed the power spectra, and we have fit the power spectra with a power law model, which is the blue fit. We can then study power spectra because they are indicators of variability timescales, and these variability timescales tell us more about the physical properties of the AGN accretion disk. So in our preliminary study, we generated power spectra of CS AGNs using the original difference imaging method. We then obtained a test sample of those CS AGN, such as the one below, which displayed strong variability and a clear power law fitting. We then analyzed three indicators from these power spectra: the amplitude, the power law index, and the low frequency turnover. And so then we compared these parameters of our test sample of CS AGN to a control sample of regular variable AGNs. And we wanted to answer the question, do the accretion disk properties of CS AGNs differ to those of regular variable AGNs? And our preliminary conclusion was that CS AGNs do not seem to particularly differ in variability properties to AGNs. And this is an interesting result, and we can see in the three histograms below, which we plotted those three parameters, the test sample of CS AGNs in blue versus the control sample of AGNs in yellow. These distributions do not vastly differ. Their peaks are roughly the same, their shapes are roughly the same. So that was our preliminary conclusion. And now for the future, we would like to repeat this analysis with Scarlet 2 generated light curves, as opposed to original difference imaging light curves. And Scarlet 2 will be very helpful because it will allow us to obtain a larger sample size of CS AGNs, which contain those that are fainter and noisier that we otherwise were not able to analyze with original difference imaging. Thank you.
What's the benefit of looking at light curves generated by Scarlet 2 instead of naturally occurring ones?
Yeah, so the light curves created by original difference imaging, let me go back to the slide here. So as we can see in this light curve, original difference imaging works very well with point sources, but when the source, the AGN source, is convoluted with other galaxies, maybe a supernova, you have a complex image, then the light curve becomes very noisy because we are unable to then separate the AGN's light from other sources. So Scarlet 2 helps because it is then able to successfully model this image, and so it knows what light is coming from what source. So we can isolate the AGN.
Questions? Could you give me a little more intuition about like what are these accretion disk perturbations that would be generating these kind of things?
Yeah, so one typical example are stellar tidal disruption events. So when a star comes too close to a black hole and is tidally disrupted, and that like gas is now added onto the accretion disk, and so we see an optical flare because it's able to produce more energy now.
All right. Thanks.